Preventing a pathogen from entering our respiratory system, at first glance, may seem obvious. The first thought might be to trap them by preventing particles from moving through a filter. But looking deeper at the problem reveals the true scope of the challenge. With every normal breath we take, we inhale around a half liter of air. The pressure difference between the atmosphere and our lungs during inhalation peaks at around 8 centimeters of water. For comparison, a typical shop vac can pull a vacuum of around 200 centimeters of water, or about 25 times that of our lungs. Pathogens can vary widely in size, with bacteria generally ranging in size from 1 to 20 micrometers, to viruses, which can range from 17 nanometers up to 750 nanometers. The rhinovirus that causes the common cold, for example, is around 30 nanometers in diameter, while HIV, SARS-CoV-2, and some strains of influenza hover around 120 nanometers. Physically creating a sieve that would prevent a 30 nanometer particle from passing through would be absurdly impractical, as an opening would only be about 200 oxygen atoms wide. Our respiratory system is simply not capable of moving enough air through such a filter. It would also be unsuitable for inexpensive mass production. Modern N95 respirators, however, manage to accomplish this level of filtration in an efficient manner which can be easily powered by our breath. Inexpensive and easily produced in bulk, they accomplish this exploiting the peculiar characteristics of particles at these scales. N95 respirators are part of a class of respiratory protection devices known as mechanical filter respirators. These mechanically stop particles from reaching the wearer's nose and mouth. Another form of respiratory protection is the chemical cartridge respirator. These are specifically designed to chemically remove harmful volatile organic compounds and other vapors from the breathing air. Both classes of respirators are available in powered configurations, known as powered air purifying respirators. These devices use battery-powered blowers to force air through either a chemical or mechanical filter, allowing for the use of more aggressive filtration. The filter type in these systems must be matched to the contaminants. The N95 designation is a mechanical filter respirator standard set and certified by the National Institute for Occupational Safety and Health in the United States. The number designates the percentage of airborne particles removed, not their size. While ratings up to N100 that can filter up to 99.97% of airborne particles exist, N95 respirators were determined to be suitable for short-term healthcare use in the 1990s. Other designations include oil-resistant R and oil-proof P respirators, which are designed to be more durable and maintain filter effectiveness against oily particles in industrial use. Surgical-grade N95 respirators possessing fluid resistance were specifically cleared by the United States Food and Drug Administration for medical use. Internationally, other similar rating standards are used to designate respirators. The European standard denotes masks as FFP1, 2, or 3, with FFP2 being the equivalent of an N95 respirator. Others, such as China, use a designation system similar to the US. Some of these standards, such as the one used by Europe, also denotes the maximum allowed inward leakage of the mask. Modern mechanical filter respirators work not by netting particles, but rather by forcing them to navigate through a high surface area maze of multiple layers of filter media. This concept allows for large, unobstructed paths for air to flow through, while causing particles to attach to fibers due to a number of different mechanisms. In order to achieve the high surface area required, a non-woven fabric manufacturing process known as melt blow is used for the filter media. In this technique, high temperature, high pressure air is used to melt a polymer, typically polypropylene, while it's spinning. This produces a tough yet flexible layer of material composed of small fibers. Depending on the specifications of the layer being produced, these fibers can range from 100 micrometers all the way down to 800 nanometers in diameter. How these fibers capture particles are determined by the movement of air through the filter media. The path of air traveling around the fiber moves in streams. The likelihood of a particle to stay within the stream is primarily determined by its size. The largest particles in the air tend to be slow-moving and predominantly settle out due to gravity. Particles that are too small for the effects of gravity, down to around 600 nanometers, are primarily captured by inertial impact and interception. Inertial impaction occurs on larger particles in this size range. When a particle cannot follow the airstream around a fiber because of its inertia, it impacts the fiber where it's captured. In the interception mechanism, smaller particles stay within the airstream, but due to their size are naturally brought close enough to come in contact with the fiber. In contrast, particles below 100 nanometers are mainly captured through a mechanism known as diffusion. Random movements of air molecules cause these very small particles to wander across the airstream due to Brownian motion. Because the path taken through the filter is drawn out, the probability of capture through inertial impact or interception increases dramatically, particularly at low airflow velocities. As a supplementary capture mechanism, some manufacturers such as 3M also employ electrostatic coatings that capture particles through charge. Though the quantity of charge and its longevity are difficult to quantify, it has proven to be a highly effective method of capture in testing. Because of the complex, overlapping methods by which particle filtration occurs, the smallest particles are not the most difficult to filter. In fact, the point of lowest filter efficiency tends to occur where the complementing methods begin to transition into each other, around 50 to 500 nanometers. Particles in this range are too large to be effectively pushed around by diffusion, and too small to be effectively captured by interception or inertial impaction. This also happens to be the range of some of the more harmful viral pathogens. Interestingly, the more a respirator is worn, the more efficient it becomes. This is due to the captured particles now becoming part of the filter medium, further offering more surface area to capture additional particles. The downside of this is that the airflow now becomes more restricted, with the mask eventually becoming unusable. Because of this, the ideal lifespan for a typical N95 respirator is about 8 hours. In addition, they are easily degraded by liquids. Even in surgical grade masks, disposal is recommended once bodily fluids have compromised them. The weakest point on any respirator is how well it seals against the face. Air will always pass through the facial leaks because they offer much lower resistance than the respirator, carrying particles with it. With substantial leaks, a respirator with a higher filtration efficiency rating may actually offer less protection than a properly fitted respirator that has a lower filtration efficiency rating. Because of this potential for operating under a false sense of security, training and constant fit and seal testing are critical to their effective use.